active Brownian particle model. So what we have essentially is the following. Let's think about a okay, let's think about a regular Brownian particle. But on top of that, they're undergoing self-propulsion, so we associate a constant speed of swimming to the particle. Because they're swimming, and then these particles will be polar. They're going in some direction. So we call that direction the swimming director Q. So this particle is then swimming with the velocity U sub s times Q. Okay, so we can write down a probability density function, which specifies the configuration of the particles. In this case, we have to specify both the position, which is the position of the center of the particle, for example, and also its swimming direction to fully specify the configuration. So then P would be a function of X, Q, and time. Okay, that's good. And then we can write down a conservation law for P. Which is called the Smoluchowski equation. That's essentially a generalized or higher dimensional advection diffusion equation, in this case in both space, physical and orientation space. Okay. And we have two flux vectors. One is in the physical space, which tells you how the particle is transported in physical space. So there are two contributions. One is due to their self-propulsion. The second is a Brownian term. Okay. In the orientation space, particle is only undergoing random reorientation that is represented by a Brownian rotational diffusion. Okay, great. So we also talked about how do we work with these operators. So let's think about 2 dimensions. So in 2 dimensions, we can parameterize our orientation vector Q in a Cartesian space X and Y using just an orientation angle phi, right? So in that case, Q becomes cosine phi, sine phi. And we can explicitly write out our orientational gradients in 2D to get the following equation. Okay, any questions up to this point? So this is what we discussed last time. And then the interesting part is if we only want to think about the number density distribution in space without caring about their orientational distribution, we can marginalize our full probability density to only look at what's called the number density distribution, which is only a function of space and time. So that will be in 2D. That's just, we're just going to integrate out the orientational degree of freedom. Okay. And in doing this, we can just integrate out the conservation equation to get an equation of the following form. Okay, so in 2D, it's quite straightforward to see that the integral of the last term vanishes because all the functions are periodic in orientation space due to the geometry. So we're left with this equation. And in writing down this equation, we introduced a new term, which we don't know yet. That's called the polar order, which is Q, P, dQ, or in 2D, that's just phi. Okay, so that's a polar order, which gives us the net orientational order in the system. And if you multiply that by the speed, that's just how much particles are swimming on average. And notice that if you look at the equation for n, it is in a conservation form, which means that we can write this equation into the divergence of a flux vector, right? J of n. So that is conserved. which makes sense physically because we were not destroying these active particles or generating new ones. That's good. Okay, so that's the number density. And we also talk about that in order to solve this equation, we need to know m. And last time we tried to derive the equation for m. So let's look at that. I'm going to switch back to my laptop. It's coming. Yeah. Okay, great. So this is the awesome. Okay, so this is the equation we're looking at. And we introduce what's called the number density and polar order, which if you think about probability, that would be the 0th moment, n, and m is the first moment. Okay. So here we've also derived the equation for n, which depends on m. So you can do the same thing by multiplying the Smolov-Shelsky equation with q, and you integrate. So I'm going to skip the algebra, but what you will discover is you're going to derive an equation for m, like you did for n. So in this case, the equation for m depends on an even higher order moment, which is called the nematic tensor. So that's a second order tensor parameter. And if you look at the equation for m, what we see is there are 3 terms, right? So if we do not have this term, then that's a conservation law for m. However, we have this 3rd term, which is a sinc term, which means that the polar order is going to relax over time. So if you think about a sinc term, in general, you can write it this way. Okay, so we have this equation for m. And let's do a simple thing. Suppose that we're in free space, so there's no boundaries, and we're just looking at how active particles are swimming around in free space. So let's add up all the polar order in space by doing an integration, right? What we can do is let's integrate out m over the entire physical space, x. If we do that, what we have for this equation is the following. Yeah. And when I do an integration of the 2nd term, what do I get? Any suggestions? Sorry? So what I want to do here is I want to integrate the divergence of Jm in position space, right? So I can make use of the divergence theorem, but because we're in free space, the boundary of the free space is at infinity, and at infinity there will be 0 flux. Otherwise, particles are escaping out of the system. So which means this term is going to vanish when we do the integration. Then we're just left with the following equation for the net polar order in the system. Okay, so that's interesting. Let's define this as m, capital M. So what we do have here is the following. So then we have dm dt. That's equal to minus d minus 1 r of m. So we know how to solve this equation. That's a 1st order differential equation, and the solution would be so where I've defined tau r to be 1 over dr.
In relation to the propulsive force you're generating.
Questions about this?
Can you particle
Sorry?
swimmer is able to self-propel
Small
in a
d,
Stokes flow.
So small d, I guess there's a conflict of notation. So the small d here is the physical dimension. So here d can be 2 if you're in 2D or 3 in 3D.
Here is the equation.
This equation?
But yes, how is it?
So to get the equation for m, what we're going to do is we're going to multiply the equation for p by the vector q, and then we do an integration. Okay? So that's, I'm not going to show the algebra because we'll do the exercise on Saturday, but you get the idea that when you multiply p by q and do the integration, you're going to get an equation for m. And I'm just, yeah. Yeah, so the reason that we have this d minus 1 here is because we made use of the general
the physical words, because if d equals t plus y equals to 1, it will not have any relation with the.
That's right. Yeah, and that's a great comment because that's the utility of the general rotational operator that we used last time, which is this one, right? Okay, so if you use the general operator, you're going to derive a conservation equation in any dimension, and the dimensionality would appear. In this case, that appears in this term, which what this equation tells us is polar order is not conserved because we have this sinc term here.
No.
Any questions? Yeah.
Tau
R is 1 over dr. So dr is the rotational diffusivity, which has dimensions of 1 over time. So tau r will be the reorientation time scale, right? So dr is the Brownian rotational diffusivity, and 1 over dr is the reorientation time. So that's roughly how long does it take for the particle to change its orientation significantly, right? So for a swimmer, it has persistence, so it goes in a certain direction. How long does it go in that direction? That's characterized by tau r, or 1 over dr.
There's two different kinds of swimmers in general at this scale. And the point is, can we, to what extent, can we represent the flow field these guys are generating using these force dipole approximations, which we know intuitively. Yeah, exactly. So if you sort of prepared your system with some initial polar order, for example, you say initially particles are just a line pointing to the right, so that would be m naught, but then that will decay away over time because there's nothing that's maintaining that polar order. Physically, what's happening is you have random reorientation, right? So this polar order, initially, every particle is a line, is going to randomly reorient. So you will lose that over time. So the difference here then comparing the polar order and the density is we know that density is conserved and then polar order is not, because polar order is not a conserved quantity. And also in general, higher order moments, so you can look at nematic order or even higher order moments. Those are generally not conserved.
So number density is not, but polar order is.
It's not. Yeah, that's a key point here by looking at these equations. And you can get that sort of from the structure of the equation. So whenever you can write a field into a conservational form, then you know it's conserved. In this case, it's not. And dr would be, or 1 over dr is the decorrelation time.
So can we take the first one and the second one space?
This one?
This is the first.
First one. No, you don't have to do any equation there, right? This is already in a conservational form. Because of this guy. So this guy is a sinc term, right? So if you think about a differential equation, you have the time derivative plus some number times itself. So that gives you exponential decay. And then you would lose that initial polar order. Okay? So let's think about
because there is some kind of rotation in the.
Yeah, there's rotational diffusion. That's why you have this relaxation of the polar order.
So I think this tower relaxes.
Yeah. So we're gonna show that in the next slide. So if you think about what's happening with this swimming, question?
Yeah, so in one dimension, no polar relativity.
So in one dimension, it depends on what you mean, right? If you're saying the particle can only go to the right, or you can go to the right and left, then you can have a binary orientational parameter, say +1, -1. That's one possibility. In that case, you have a discrete state of orientations. So in that case, you have to rewrite the equation slightly, but you can still have the same kind of structure. Particles are flipping, right? Left and right. So they swim towards the right, say for some time, and then they will randomly flip to the left, and then they'll go left. So that's also possible.
And polar being conserved again.
No, polar order wouldn't be because they're still relaxing, right? They're hopping from +1 and -1. So if you initially all particles are pointing to the right, then if you have random flipping, then at long times they're all gonna decay away, right? So the average would be zero.
Last slide.
Yeah.
Yes, so in the second equation there's delta danger. If H1 t equals to 1, the same term disappears.
No, you can't write it this way for 1D because we're doing continuous Brownian reorientation.
So there should be another term.
You have to rewrite the first equation. So here, so this doesn't apply in 1D. That's a continuous operator. What you have to do is write a rate in term. That's why you can recover the special case, which is 1 dimensions. But if it's higher than 1D, it's 2D, 3D, or n dimensions, it will work fine for active Brownian.
You know, say that B sin T equals.
No, you can't. So because the active Brownian particle model would become degenerate in 1D, right? You can't have continuous reorientation.
In 1D, it can still happen work like.
Yeah, but but the state of the orientation is discrete, right? Yeah. So you just have to rewrite the operator, and then you will recover a similar equation, but we won't be this equation. Yeah.
We can wrap that from this thing. I could have a relate like this from the 1D.
Yeah.
You get this one.
You can scaling wise, you could in terms of the time scales involved and what's the behavior of the system. Yes, but mathematically, it's slightly different. Later on, we'll also talk about Raman tumble particles, where you also have a discrete orientational sort of reorientation events, and then even the mathematics is different, but the physical behavior would be similar, which is what we are going to talk about later on. Other questions about this? Yeah.
One thing as we speak there, just basically random law.
Yeah.
Yeah, it is already covered in the crankcase. Now it has some edge.
Mm-hmm.
Because the said is to have a pistol eating one day.
You won't be a rotation, it will just be a time scale that defines how long does it take for the particle to change its orientation from +1 to -1, or vice versa.
That we learn, I didn't just put in the random what.
You can, yeah, you can. That's why it becomes degenerate. So the active Brownian particle model, which is a continuous model, becomes degenerate in 1D. But what I'm going to show now is that, yeah.
It doesn't make sense of activity in 1D, right?
You can have activity. You can still swim, right? You can
like consistent and what's.
Yeah, you're swimming, yes, in a straight line, but you're changing direction. You still have activity, yes. Yeah. Other questions, comments? Okay, great. So let's think about a particle that's undergoing this active motion, right? So as we're getting into this one, what happens is the particle is taking a step in some direction with the speed u sub s, and then the time it takes for this to persist is a reorientation time tau r, right? That's defined by 1 over dr. So after that, roughly the particle has changed its orientation significantly, so it's going to now swim in a new direction, and then it's going to take a new step for the same amount of time on the time scale of tau r. After that, it will take a third step, and so on and so forth. So what happens if you look at this dynamics at a time scale that's much larger than tau r? Any suggestions?
Becomes a problem.
So we're now thinking about what happens when you look at the system at the time scale that's much larger than tau r, so at long times, which means first is the particle has taken many steps, right? Has taken many steps of reorientation. What that gives you then is it looks like a random walk now after long times in 2 dimensions, in a plane, for example. And for any random walk, we can associate a diffusivity, which is just defined by the step length squared divided by the decorrelation time. So that means that we call this the swim diffusivity because that's due to the swimming motion coupled to random reorientation. So then if we make use of this random walk perspective, then we say that the swim diffusivity, it must scale as L squared over tau r. L is the step length. And L is just the swim speed times tau r, right? Then you have the third relation, which is that this swim scales as the speed squared times tau r, where I've just rewritten the step length by the velocity times tau r. Okay, so that's interesting because if we are thinking about active Brownian particles, these particles have Brownian regular diffusion, but on top of that, there's this long time effective random walk, which means if you were to measure the diffusivity at long times, we're not going to get back the Brownian value dt. Instead, we're going to get is an effective diffusivity, which is the Brownian value plus this swim that we just talked about. So which means if you have swimming motion, you're going to get enhanced diffusion at long times. So that's a very important concept for active systems. Any questions, comments on this?
Why, like, in a normal Brownian particle, we should have just what dt then?
That's right.
So,
So if you set this to 0, you recover dt, right?
so in long times, even if it looks like a Brownian particle,
It looks like Brownian. At long times, it looks like it's just doing diffusive motion, right? But the diffusivity is higher than a Brownian
it comes
particle.
from the math intuitively when we think about it. Like,
Sorry?
obviously, it comes from the math, like this thing.
Yeah.
It comes up from the math. How to just think of it as intuitively, like how the US is activating? Because if you look at the
This is physics. I'm going to do the math later. So this is a physical argument of the stepping, right? So it's if you have a random walk, the question is how far do you spread over time, right? And the definition of a diffusivity with that is just either the step length squared over t or the speed times the time, right?
proposed the time, right?
Right? Yeah, or dimensional argument. Yeah. Other comments?
So
Yeah.
Is it helpful because, like, is it important, this be effective? Is it because you can calculate these from the D-swim that you can get the tau, or like I'm trying to
I mean,
understand
whether
the importance
these
of-
when we because this will govern the dynamics of active particles. It will be different, right? Which we'll talk about later on. But if you're thinking about measurements, so what are you thinking about measuring in this context?
I'm thinking,
Yeah.
let's say you've not waited long enough.
Yeah.
The system is not ground
Mhm,
yet.
mhm. Yeah.
We already have the information of D-swim there, right?
So yeah, the physics is there, but it hasn't manifested as a diffusive process. So this diffusive process only emerges after long times.
I see.
So there is a few caveats to this, which means that if you want to measure the diffusivity of the swimmers, it depends on what time scale you're looking at, right? So the time scale that you're looking at gives you different behaviors to the system. Yeah. Other comments, thoughts? Yeah.
But in this case, there is a fixed statement that you were saying.
Yes. Yeah, that's L.
So, just by putting that, how is it really from the not the random perspective?
It's not.
Because in random also there is a fixed statement.
It's not. Yeah.
Is changing the direction random.
It's not different.
Good.
That's the point. It's not different. It's only that the origin of this random walk is from swimming motion. It's not. Once you map it to a random walk, it's exactly what's happening.
Skip the order of this statement for a particular biological system or
What is the
order of this statement that is that you
order of L? L is the swim speed times R, right? That's the
it's like what is the length scale?
what is the length scale?
length scale of.
Like in realistic system, or what can be the length? You know?
So you would take the swim speed. You take a bacteria, for example, which typically has a speed of a few microns per second, and their rotation time is typically on the order of seconds as well. So it's about a few microns. Yeah, for bacteria. Other things may be different, but that's roughly how large the step is. Yeah. Other comments? Okay.
Short time we have a different kind.
If you look at this as you mean a time shorter than tau r. Yeah.
We see this types where the tower is just ballistic, right? Because we don't have.
Yeah, from this sketch you can see that it's just going straight in some direction. That's correct. Yes.
But say we, like as you said, that if you don't make that plus right,
Then you don't get a diffusive behavior. Right?
you need to make it more way that it was like.
No, you don't need to make it to go. It's we're just trying to analyze the dynamics of the system, at long times.
So maybe it not step as an accident.
Because the time scale is only a second, you're not gonna do experiment just for 1 second. So the point is, in a regular experiment kind of setting, it's almost always long times. Yeah. Other, yeah.
I have a very nice question.
No, go ahead, please.
To figure out the dynamics of the system, what
Yeah.
are the things that we need to automation?
For this model,
Yeah.
you can actually solve this. You can solve the full equation in free space. You will have a, for example, mean square displacement over time for all times. Then you can look at how that behaves over time, which we're going to do one of that exercise on Saturday. In terms of the diffusive behavior, you can get all the behaviors you want. You can look at the mean displacement, mean squared, and all moments of it in this model. Without other forces or boundaries, you can do that analytically. But the point is, we need.
If you calculate the effective,
Yeah, because if you don't have US, then you have your Brownian system. It's zero.
we need to measure that. Like if you are
In experiments, you can easily measure the swim speed. Yeah.
I mean, once we figured out what kind of dynamics is happening at that particular time scale, it's way easier to calculate the mean displacement, right? Like for example, when it's diffusive, the
Yeah.
mean displacement.
Yeah. Of course, in experimental measurement, you could just keep track of it over time, and then the point is, how do you understand what you're measuring? Then you have to understand what happens at different time scales, and then compare that to your experimental time scale and measurement. Then you can make sense of it. That's another way of thinking about it. Other comments?
That's it.
Okay. Great. So let's talk about one thing here, which is, so since we're talking about different time scales, so if you look at times much smaller than tau r, right, when t over tau r is much less than 1, from the swimming motion, we see that it's going in a particular direction ballistically, which means if you're swimming in a certain direction, what does your displacement go? It goes like the velocity times time, right? What about square displacement? That's the velocity squared times time squared. So you would have a quadratic term here for the short time. Of course, you still have the linear time because you still have the Brownian part there. But if you think about active systems or these active particles, their speed are often quite large compared to their Brownian diffusivity. So roughly speaking, for short times, what you're observing is a ballistic behavior. So it goes like t squared. And we talked about the long time already. So at long times, then if you measure the mean square displacement, it's going to be diffusive. However, the diffusivity is not the Brownian value. It is an elevated effective diffusivity. So tau r essentially sort of defines, the important time scale in the system that gives you the transition from ballistic to diffusive behavior over time. Any comments on this?
So one thing I have to ask you here, as he said that your tower is a critical time at which it relates to the rotation and the future.
Yeah,
So this is less than tower.
that's correct.
And there is much more than tower.
That's
What
correct.
if you measure at tower? What will happen?
If you measure a tau r, you are at the transition zone, right? You interpolate between these states.
Okay.
Yeah, it's a continuous transition. If you look at the mean square displacement over time, right, it transitions from a quadratic to a linear profile. You're just at the middle. Yeah, but you can't measure anything at a particular time. If you're measuring, the slope, you can have one point, right? If you're thinking about you plot mean square displacement over time, you can't measure at one particular point. You always have to interpolate, the slope of it. To do that, you need to know what's the scaling behavior in that regime. Other comments? Okay, so let's look at this video here where what's happening is there is a trap which is going to so initially in the experiment, all the active particles which what you're seeing here is the bright spots. They're all trapped in the middle of the domain. And so in the experiment, so initially they're still aggregating active particles to the middle of the center of the experimental device. And what happens after some time is we're going to turn off the trap. So when the trap is on, these bacteria cannot wander about too far away, okay? And what you see here is once you turn off the trap, these active particles explode. So what you see there, let's watch this again. It happens at a very fast time scale. That's why it's quite hard to see here. Okay, so you see that? once you turn off the trap, almost immediately these active particles they run away. And again, because typically for these bacteria, tau r is on the scale of 1 second. Once you turn off the trap, they're gonna swim, and they quickly transition from a ballistic to diffusive-like behavior on that time scale. So if we look at stationary,
1 second can be still very large if you talk about other systems.
Yeah. It depends on what you're looking at, of course. Yes. So here's a still image, which is easier to see. So these are experimental images. So here's a time 0. The trap is on, so particles are aggregated in the center. And once you turn off after this frame, turn off the trap, these particles are going to swim in all directions. And initially you see sort of ballistic kind of behavior, but quickly after 4 seconds, you're transitioning into a diffusive behavior. In the last image here, you're seeing almost already a very homogeneous distribution of particles. So in that case, you're already in the diffusive regime. Any questions about this? Yeah.
It's more personal the previous slide.
Previous, yes.
So why do we take x into x and then increase?
Why do we take?
X into x and then average it.
So that's the mean square displacement. Yeah. So
it's just a rotation.
what is rotation?
Just a rotation.
Yeah, so the bracket is the averaging of 2x. So 2x, that's a product, so that's mean square displacement, which allows you to track if you track the scale, if it's diffusive, right, you will go linear, and then the coefficient is related to the diffusivity. And there's a numerical factor which depends on the dimension, but other than that, it's a mean square displacement. Other comments?
So, sir, the experiment that I think and this affecting diffusion rate in detail and then as you selected just type the version and crossing all times it's in so tell me those unusual how we at least make this.
Oh, you track the position of each bacteria. That's easy to do in experiments. One simple way is you just do optical imaging. You track each particle, right? Then you can chart out their position over time for all particles or the particles you're looking at. Then from that you can calculate the mean or the mean squared over time. So that's an easy thing to do in experiments. And then you can figure out the effective diffusivity by looking at the slope at long times. Yeah. Great. Other questions? Okay. So if we think about the transition, what you can do here is, we're not going to derive the equations here, but what you can do is you can derive a telegraph equation for the density of these active particles, making use of the ABP model we talked about. People have done that, and here's the equation. So if you look at this equation here, what happens is, if I remove this term, what kind of equation do we have? Any? I remove this one. What equation do we get? It's a wave equation, right? So what if we remove this term? So you see, mathematically, you have a telegraph equation which have both wave-like and diffusive-like behaviors exactly manifested here. And what is the time scale here that you see in this equation? Forget about the dimensionality. The only time scale is tau r. So that's the transition, right? So you see that both physically and mathematically, you can work this out quite nicely for this model. And here's a simulation of that PDE, right? So over time, so initially you see these wave-like rings that are expanding out on the time scale that's shorter than tau r. Once you cross tau r, it quickly becomes diffusive, and it just spreads out diffusively at long times. So that's a typical behavior of this kind of systems. Are there any questions about this? Okay, that's great.
When the tower is small, then we when T is less than tau r, then we see.
That's right.
Yes. So then tau is huge and that terms and
Tau r is huge.
like if you say that it makes a big factor.
Okay, yeah.
That tau is
Yeah, that's right. What does it mean for tau to be huge? It means you're very persistent, right? Because you're swimming in one direction for a very long time, then you're stuck in the ballistic regime. Yeah.
It's
And if we need multi-particles, then we use polarity.
Multiple particles.
Multi-infected particles.
Yeah.
Then we include the polarity of one particles.
Yeah.
Okay, then is a tower affected like relative decreases?
So right now we're still looking at dilute or one particle system. If you have multiple particles that are interacting, you still have this kind of behavior. However, it won't be a simple structure like this. So you can still write down an effective equation, something like that. But then the time scale there depends not just on their one particle hour, but also on the interaction of particles. Yeah.
So that can be ready.
Yeah, that can be done in with some sort of coarse-grained model, but it won't be as simple as this. But the phenomenon will persist whether it's one particle or multiple particles. Yeah. Other questions? Okay. So let's think about one thing. So there's another, okay, here's some math that's involved with this. So what we can do here is the following. So let's look at the number density field, and let's take a Fourier transform from real space to Fourier space. Okay, so that's what I've done here in the first equation. So in Fourier space, what you can do here is you can show that you can write down the equation for the Fourier transform number density in the following form, where k is a wave vector. Okay, and if we stare at this second equation, can you tell me what kind of equation is that? So what type of equation is this one? I guess the answer is given there, but why is that an advection diffusion equation? Any suggestions? Yeah.
And it's with that. So electromagnetic.
Yeah, this appears in many places, but so let's think about a general advection diffusion equation for a moment.
Yes, done. Yep.
Okay, so let's write this down in real space, right? So that is an advection diffusion equation. So U here is a advective field, for example, a fluid velocity, something like that. So that's advection. Here, that's diffusion. Okay? But if you do a Fourier transform of this equation, what happens when you do a Fourier transform? What happens to the derivative? Yeah, question?
What does advection?
Advection means particles that are just carried away by some field. For example, in a fluid, in a flow, in a river, right? You have some particles in the water, it's going to move with the flow. So that's advection.
That's intelligent.
So it's in the flux. So you should, it's best to think about it in the following way. So you write this in a conservation form, again, as we did before, right? So then you think of the flux. The flux tells you how the particles move around, okay? And then in this case, we have two terms. And how does the particle move? The first is I'm moving with the velocity u, so that's advection, right? And the second is I'm diffusing. So the interesting point about the Fourier transform is when you take a Fourier transform, what happens to the spatial gradient operator? Or the derivative? Sorry? Yeah.
Or as in like.
Yeah, so the differentiation is gone, right? It becomes an algebraic multiplication by IK. So that's very nice. And so if we do that to this equation here, then what we have is the gradient operator becomes just IK. Depending on notation, so the notation I'm using here is e to the minus ikx, okay, times function f dx. So that's my Fourier transform. To f hat. So the derivative, the gradient becomes ik, And then what I have to do is take the Fourier transform of this vector j, right? That's how we do Fourier transforms. So if we do that, let's assume u is a constant. Then it's just Fourier transform of n. And then here I also have a gradient, which again becomes ik. N hat. So I'm now gonna put that into the bracket here. Okay, any questions about this part? Great. So we have now the advection diffusion equation written in Fourier space. We also have the real equation, which we started with. But the interesting point here is in Fourier space, you can read out the velocity and diffusivity by looking at coefficients in orders of ik. So if the coefficient in front of ik, that is the advective field or the drift velocity. The coefficient in front of, there are two iks, right? Ik dot ik, so that's the diffusivity, which means that if you write down a general equation for anything in this form, you can read off the advection and diffusion from that equation.
Here, the Brownian, it's like, because this is the Brown, this is the ATL, the affecting rate. We should just a bit too late.
Yeah, I'm just introducing this notion of, yes. So now I'm going to come back to the equation we're looking at on the computer.
So there should be an experimental reason for, or like, also let's waiting it from this video first, Mike.
Yeah, I'm gonna get to that later on. Yes. So here, what people have shown is you can write the number density field at long times. This is written in the following form, and then you can read off the coefficients, and then the coefficients that's dotted with ik is the average velocity or the drift velocity, and there's a nice structure here. So the velocity is given by the swim speed times m, which is the average m naught. That's the average polar order. So that term is just the net swim velocity, right? So that makes sense. So I have just active particles in free space without flow or external influence. The only possible origin of my systematic drift velocity has to be coming from the net swimming velocity. And it's also nice that we have this structure for the diffusivity, the effective diffusivity. It has two terms. Again, one is the Brownian value, which is isotropic. That's multiplied by the identity tensor. And the second part still has the swim speed, but it's modified by this m tilde. M tilde is the fluctuations in the polar order. So that's by removing the average, and that's the fluctuation. So it tells us that, yeah.
Also because we have to see like m and n, but this a plot and it.
Yeah, that was explained. M naught is the average polar order in a system. M tilde is the fluctuating polar order. So that's by removing the m naught. That's you're left with the fluctuation. So the point is that the average polar order gives you the average swimming velocity, and the fluctuations gives you the diffusion. Other questions about this?
Damn. You should.
And if you carry out this calculation by evaluating these terms, you're going to get back the swim diffusivity that we just talked about. Okay. So we looked at active particles in free space without the influence of any external effects. So let's think about external field. So in this case, I have a external field in the z direction. So what happens, this field is only an orienting field. So it exerts a torque on the particles or an angular velocity. So in this case, it's in this form. So when your swimming direction is aligned with h, you don't get any angular velocity. If your orientation deviates from h, you have a non-zero angular velocity, right? So that's an aligning field. So we're trying to align.
Is it 21 of this?
Yeah, it's 3D. It doesn't matter. It's a sketch. You can do this in 2D as well. So you would have an angular velocity due to the field. And what happens in this case, if you think about the average velocity of the particles, because we're trying to align them towards a definite direction, is there an average velocity in the system? So now we have, so previously we're looking at active particles in free space, right? We understood that after some time, at long times, it's diffusive. but there's no net swimming velocity because it's randomly uniform. Now we have applied an external field that tries to turn all particles in a particular direction, say in the z direction. What happens to the average velocity at long times?
This shrinks up so right moving is bias invested.
Yes, so that's what you see here on the right. So I'm measuring the average velocity in the system. You parallel, that's the average velocity along the field direction, divided by the swim speed as a function of chi r. Chi r is just the sort of the strength of the field, non-dimensionalized by the reorientation time tau r. So if chi r is 0, I get back my active Brownian particle result, which is there's no net velocity. As I increase the strength of the field, I'm going to pick up a net velocity, right? Because I'm trying to align all particles in one direction. So what's the maximum velocity I can get from that? Sorry?
Story. Scale of
So
systems.
so yeah, so the maximum would be the swim speed, right? So the only origin of velocity is my swimming velocity, but without the field, I'm randomly reorienting. Then on average, I'm not going anywhere. But if the maximum you can do is suppose that all particles are aligned in one particular direction, then what's the velocity in that direction? That would be u naught here in this case. So that's the swim velocity. So that's the maximum you can get. So in this case, as you can see, as you increase the field strength, eventually all particles are aligned. In that case, then you just get a swim speed out of it. Essentially, you've suppressed their random reorientation because you have a much stronger external field that just tries to turn them back whenever they deviate from this orientation. Any other comments about this? Okay, that's great. So let's look at the plot here on the left. So here I'm looking at the long time effective diffusivity as a function of this field parameter. Again, when the field parameter is 0, I get back the result we had before, right? The question here is, when you have an aligning field, the diffusivity will become anisotropic because there's bias in the directions. So if you were to measure the mean square displacement along the field direction, that would be different compared to the case where you measure that in a direction that's normal to the field. So that's what we see here. There's two lines. One is parallel, so that's measuring along the field direction. The other one is perpendicular. So one question here, let's think about is it easier to diffuse along the field or perpendicular to the field when there's a field present?
Hi, parallel.
Parallel or perpendicular? Any reasons why? Do you see perpendicular or parallel?
It's very
Parallel. Any reasons why that's the case?
stuff. It's like starting phase of the series.
Yeah, but remember we're looking at the diffusion, so the pushing, that's the average velocity, right? We have to remove that when we think about the diffusive dynamics. So it's once you remove the net velocity, the spreading, right? The random spreading is the diffusive part of the dynamics. Any other suggestions?
I think. In parallel in relativity.
Yeah.
Parallel to the swings, but the energy is this certain big energy.
The particles in beginning it is working in one direction.
Sorry, could you speak louder?
It is swimming in one direction. If the ends of to realize it in
Yeah.
that direction, then it will not get disturbed like later it will behave.
So you're thinking about the very strong field limit, is that right? When they cannot deviate. Yeah, so that's correct. So if you're thinking about when the field is very strong or when this tends to infinity, what happens to the diffusivities? They go to 0, right? So that's why I say the plummet at large chi r, that's correct. And then the second point here is what you see is in the normal direction, it's larger for finite field strength. So that's an interesting result. Does that make sense? Any comments on this?
What is the y-axis?
What's sigma?
Sigma. Yeah, that's something else. So forget about that. I'm taking that from a paper.
That glossy.
So that's the diffusivities. The effective diffusivities in the direction, in the parallel direction and the normal direction. That's just the diffusivity. So the diffusivity along the field direction is actually smaller compared to the normal direction. In the case of a field, a lining field. Of course, eventually, when the field stress is very strong, both of them are gonna plummet because you're not allowing the particle to fluctuate anymore at large field strength.
Yes.
Any questions about this? Yeah.
Take a larger diffusivity means if there are harder happening.
So now more fluctuations, more rushing fluctuations means about less diffusivity. Right? Yeah. Because if you see it's not really fluctuations, right? I mean, the positions like this. It's actually easier for them to fluctuate in the parallel direction, in the normal direction, because the field is in this other direction. It's not in, yeah.
She's saying this because it's emanating towards the parallel side.
Yeah.
So it cannot fluctuate the bank direction.
Yeah. So in that direction, it's less, right? Yeah. 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 So it's not about whether the velocity, whether the net velocity you get. Of course, you get a large velocity in that direction, but that's the mean dynamics. And then the diffusivity is on top of that. It's the fluctuation. Yeah.
That direction with the fusion.
Yeah, you're suppressing it. Yeah. Yeah. That's right. So it's anisotropic if you look at the different directions.
So when we lost in the other part.
So if it's easier for them to fluctuate, then which means there's a larger, there's a larger diffusivity, right? It's easier for them to move around due to diffusive motion. Yeah. It's harder for them to fluctuate in this direction because the field is constraining them.
Yeah.
Yeah. So which means the diffusivity in that direction is lower, right? Yeah. Other comments? Okay, so I think we should take a 5-minute break. Then we eat.
To take back.
Sorry? Oh yeah, that's fine. Yeah, I'm getting close to my time, so we started early. I'll leave the 4 minutes for questions.
Yes.
Yeah, yeah.
Sure enough. Yeah.
So one day, the twin, and the point of popularity is to create still. Maybe with that in this time is that we can.
Right. It does. Yeah.
It's really right to put it.
Yeah, you can manipulate their behavior in general, both their. Yeah. So you can do that. Yes, you can do that. Yeah.
But then said, actually, I particularly taught us sometime between the being non-musician was it basically what it is called. That is so that much sad. So I seen we get this stuff in way.
Yes.
Yeah, described as a fusion.
Yes.
At the end of the day, I'm not working it as a fine color thing, but I'm going to know that it's not. See. Then.
So, but the swimming direction is a random variable.
You should yeah.
On that force, and it is in addition. This year, I trigger the little dash.
Yeah. Yes. But of course, how much you get depends on how strong the field is, which is what we looked at here. Yeah. Yeah, yeah.
That's about there.
Yeah, yeah. Because the reason for that is the swimming. So you can compare. That's what this term here is doing, right? So there are two scales. One is the strength of the field, which is essentially a time scale. You can compare that to tau r. If the field dominate, then you get all particles are essentially just aligned. Then, yeah. Okay, no more questions?